Today I'm going to be covering 16.6, integrals in mass calculations. I think the title of the section is just a little bit misleading because it's true we are going to figure out mass, but kind of more importantly, and actually also the slightly more difficult thing that we'll be dealing with is locating what's known as the center of mass. Um, Well, the classic example of this is, you have a beam that is supported somewhere in the middle, and there's a heavy object on one side of it, and maybe a lighter object on another side of it, but the lighter object is a little farther from the fulcrum, or the point that where they think. So as it stands right now, this would roughly be balanced, I think. You could sort of picture this in the playground setting, right? One of those seesaws or teeter-totters where you might have kids of unequal weights, and you put the heavier kid in a little closer to the point where the thing balances, and they'll both be able to enjoy the ride. So that's what center of mass is about. If you didn't have this fulcrum here, you just had this beam with two weights on it, you'd like to locate the point on that beam where the thing would balance. So, you imagine sliding a fulcrum back and forth until you get it to balance. And yeah, it would probably go in roughly where I had drawn it originally. Another example, and I tried to make one, but it turned out kind of kludgy. Usually, I've seen better jobs of this in the sense that they fool the eye better. But a two-dimensional object, usually made to look like a bird, but mine doesn't anyway. The point of it is, it's supposed to balance at a spot that you'd be surprised by. In this case, it balances rather well on just that little point, because it's got stuff that sticks out that way, these things that look like wings. So the center of gravity of an object need not be inside the object. If I snip that little triangle off of there, the thing would balance on a point that's not on it, so it wouldn't balance anywhere on its own materials. So how do we go about actually locating this position where the mass can be thought of as concentrated, the center of mass? In this kind of setting, you have basically four numbers. You have the mass of this block, call it M1. It's actually the force that's produced by the mass times the acceleration of gravity, but it's proportional to M1 anyway. And you have the force that's created by M2. You're also going to have a distance, x1, that's how far is mass 1 from the center, or from the point of where it all will balance. And another distance, x2, for how far is the second mass from the center. And these guys are in equilibrium. The thing balances, provided that the products of the masses times the distances come out the same. So it balances if M1 times x1 is equal to M2 times x2. These kinds of things, a product of a mass, or honestly, what we really want is force, but that's fine. The product of a mass times the distance, which is on either side of that, those things are known as moments. Later on, if you go into things like strengths of materials, you'll get into things like second moments. Statisticians talk about second moments and third moments and nth moments, but moments are going to be enough for us to figure out center of masses. So that's the idea. It's a mass times a distance. That's a moment. In fact, there's names for the pieces of it. These x's, those are called the moment arms. Fairly antique language. So I wanted to show you an example of why we care about finding center of mass, also known as center of gravity, although that's slightly a misnomer. And it has to do with aviation. So let's draw a small airplane's rough plan. I'm talking about the kind that is flown by, private people, not like a military jet or a commercial airliner. The lift is generated in two different places. Actually, it's kind of surprising, I think. There's a wing, usually like there, and then there's also a small thing known as an elevator in the back. And well, it may surprise you that this guy is designed so that it generates an upward force, but this one actually generates a downward force. It's small, actually a lot smaller than I just showed it, but a small downward force. The elevator is canted so that it's holding the tail down. And why does it do that? Why do they design airplanes in this way? Well, it's for equilibrium. You see, if the airplane's nose goes up, that is, this thing comes down, well, it rotates mostly about the center of gravity, actually. It rotates a little bit, and so if the airplane were in this sort of bad orientation where it's about to stall, it's less looking like an airplane now and more looking like, I don't know what. I'm sorry. I don't need to be that accurate with it. But if it was up like that, this guy would now be like this. And the wind running into that would now be generating lift. In fact, what happens is the downward force decreases as the airplane rotates upward. Now, of course, if the pilot wants it to rotate to the upward position, he adjusts the angle of this thing. That's what pulling back on the wheel does. You change that angle slightly. But if you're not doing anything and you end up, for some reason, getting into this nose-up position, the lift on the elevator will, or rather the down force on the elevator will go away. It may even turn into a lift, and so the airplane will return to the position it was in. Right. So you want there to be a small negative force back here and a large positive force from the wings up there. That's the way you want things to be. And if you put stuff in your airplane, like people or luggage or the fuel, in such a way that you get the center of gravity on the wrong side of the center of effort from this thing, actually where I've sort of drawn that pivot spot is the wrong side. You want this to be necessary for there to be downforce from the elevator, which means that the center of gravity needs to be out there. And if you load up the airplane in such a way that the center of gravity ends up back here, then in ordinary flight, the elevator has to be providing lift. And now you're in a situation where the changes that happen by, that normally make the airplane stable don't happen anymore. So moving the center of gravity the wrong side of the center of effort of the wings is extremely bad. It gets you in a position where you have to manually control the flight of the airplane. You can't just let it go. You don't want to be in that situation. So pilots routinely calculate the moment arms and they're told what the moment arms are, and then they supply the masses and do a calculation to make sure that the center of gravity is where it belongs. It needs to be within it's about 10 inches probably of a particular location. But if it goes too far off, it can be hazardous. Okay, so how does anybody calculate a center of gravity? You start with just an arbitrary coordinate system. If it's an airplane, the plane that is usually used for that arbitrary coordinate system is it's called the firewall. It's a wall that is between the engine and the occupants of the airplane. I'm talking about the kind of airplanes that have propellers, single engine airplanes that not private people fly. Anyway, wherever you put that arbitrary point, you begin measuring things from there. So for each object on the plane, you'll have a moment arm and you'll have a mass. And there may be multiple objects on the plane. There you might have, like up to a triangle here, that has moment arm x2 and mass m2. And let's put a third thing. How about a square now? Oh, where can I draw it? Well, I'm going to draw it down here, but its moment arm will be x3 and its mass will be m3. So suppose those three objects, the filled in circle, the triangle, and the square, are sitting on a line. Now, all told, they have a mass, that is, the total mass of the three things is m1 plus m2 plus m3. And the center of mass of these things, probably, it depends on what the masses are, of course, but the center of mass is actually, there's a symbol people use for it. Looks like a circle with a crosshairs in it, but then two sides of it, two of those wedges are colored in. You see engineering drawings, they use this symbol to show you center of mass. Anyway, that's located somewhere. Let's call that position x bar. In fact, that's what everybody calls it, an x with a bar over it. Sort of an average moment arm. So the center of mass, how do we get it? Well, the idea is this, that if you put all three of these masses at that spot, it would produce the same moment as they do in their individual places. That is, m times x bar should be equal to m1 x1 plus m2 x2 plus m3 x3. So if you add up all the moments, you get something that's the total moment, let's call it. And that should be the total mass times the moment arm, or the location of the center of gravity. If you're truly looking to solve for the center of gravity, what you usually do is calculate this total moment and divide by the total mass. Or if you like, you can write it out as the sum of the things. In fact, that's maybe a nice way to write it out as the sum of the moments, the sum of the masses, because you see a certain parallelism between what's in the numerator of this fraction and what's in the denominator. The numerator is the sum of the moments. The denominator is the sum of the masses. Maybe we should do a quick calculation of this sort in real stuff, right, with some actual masses involved. So at 1 meter away from 0, or position 1, we're going to have a 3 kilogram mass. At 4 meters away from the center, we're going to have a 2 kilogram mass. A little bit smaller, yeah, a little smaller. And how about at 2 meters away from the center, we'll have a big 5 kilogram mass. So it's quick to see that our total mass, m, is 10. Let's add up our moments. This 3 kilogram, 1 meter away from 0, gives us 3 times 1. All right, fine. 5 times 2. And finally, 2 times 4. So the total moment is 3 plus 10 plus 8. 21. The total mass was 10, so the position of the center of gravity, x bar, is 21 over 10. Or what is that? What is that? 2.1. 2.1. So this thing would balance, if we split the region between 2 and 3, try to find, yeah, that's the spot it would balance right there. A tenth of a unit away from number 2. Almost, but not quite, dead under the 5 kilogram mass. All right. Well, how do we relate all this to calculus? These are sums, these moments that we've been doing. The usual metaphor or analogy is that sums, when you pass to the limit, when you move from discrete things at discrete locations to continuous things, sums turn into integrals. So let's do an example that's still one-dimensional. It will be along a line, but what we want to do is, instead of thinking about discrete masses here and here, there's a continuous spread of mass. The thing is made out of something, and the density of that something tells you how much it weighs. This is an example of that kind of setup. It's essentially a one-dimensional thing, but it's needle thin at one end and it's large at the other end. So while it's one-dimensional, how to say that better? It is one-dimensional, but its density changes across the span of it. Its density is 0 at the tip here, and its density is, I don't know how much cardboard weighs, but some palpable amount at this end. In fact, you can see it changes linearly. I've got this thing tapering in a linear fashion. So where along its length do you imagine it would balance? I think it's pretty clear it's going to be closer to the fat end than it is to the thin end. I bet it's, nope, not there. Okay, that's about right. So how can we do that sort of calculation as an integral? Well, what we want is, instead of adding up discrete masses, we want to integrate differential masses. So dm is going to be differential mass. And if I'm thinking about a setup where I've got a linear object, let's say it goes from 0 to, I don't know, 10. My thing was bigger than 10, but whatever. It's got a density that we can plot. So suppose the density is like, oh, by the way, in engineering and science, most often people use the letter rho for density. That may seem confusing since we just use rho for radius in spherical coordinates, but if you want to use d for density, that's nobody complains about that either. The sort of tapered triangle-y shaped thing I had started with a density of, I don't know what it is, but it certainly goes down to 0 by the time we get to the end of it. So a density that looks something like that. Well, what is differential mass in this kind of setting? For each small unit of length along the position, some change in the x-coordinate, we have a sort of a little density times length calculation. If you multiply the density times dx, I mean, yeah, you think of it as area under the curve, but that's a density times an amount of the material. That gives you the mass of that much. The mass is going, of each little chunk is getting smaller as we go down, starting at something big and getting smaller. So differential mass is rho times dx. If I just integrate, in this case from 0 to 10, the function rho times dx, I'll get mass. That is, I'm trying to get you used to the zen of this, that if you need to get a quantity, you integrate the differential version of that quantity. So what is the tiny little bit of mass that each microscopic part of the length of this thing contributes? That's dm. When we add up all those infinitesimal pieces, we get m. let's just make this a little more concrete here. Suppose this density started out at 1 gram per centimeter. I've got a thing 10 centimeters long. At one end it's 1 gram per centimeter, at the other end it's 0 grams per centimeter. It's tapering off to 0 at the end. Then what is this function? What is this function rho? It's actually going to be 1 minus x over 10. The y-intercept, it's a line, right? The y-intercept is 1 and the slope is minus 1/10. Okay? So for our actual calculation of the mass here, we would have integral 0 to 10 of 1 minus, let's say it is 1/10 x dx. If I wanted to find the moment of all these things, of all these little differential chunks of mass, that would be differential moment I'm looking at, which I would probably call dm. Let's just keep that stuff and think about what dm would be. Differential moment. Well, that is x times dm. It's the position you're at times the amount of mass that's at that position. But you can also expand it out as x times rho times dx. And I feel a little bad about this, so I'm going to fix it. I'm going to fix this right now. Rho isn't a constant, right? It's an actual function of where we are along the length of this thing. So I should really write rho of x and then dx. And that should have really been rho of x too. That's why the thing in here became an actual function, not just a constant. If rho was fixed, it would be better notated that way. But if you think rho is variable, then like that. So what if we want to find the total moment? We're going to integrate the differential moment. So m, the total moment, is going to be the integral. Let's do the integral from 0 to 10, just like we did here, of x times rho of x dx. So we're actually at a position now to literally calculate the moment, the center of gravity of that triangle. Somewhere along its length, you have this density function. If you integrate that density function, you find the mass. Let's do it. Then we're going to need to also integrate the x times the density function to get the differential moment, or sorry, to get the moment. What we're after in the end is that x bar times m should give us the total moment. That is, x bar times little m equals big M. Solving for x bar, it's just x bar is m divided by m. Sounds bad when I say that. Total moment divided by total mass. I'm not sure whether it's worth it to erase or not. Yeah, let's see if we can just squeeze it in here. Let's integrate that. That's trivial to integrate. You get x minus 1/10 x squared, or, sorry, 1/10 x squared over 2, so that's x squared over 20. All evaluated between 0 and 10. Let's see, this one is 100 over 20, that's 5, and this one is 10. 10 minus 5. Okay, 5. Does that sound about right? If you want to estimate this integral here, you should notice that if I made a corresponding triangle that was just the same thing but flipped over or turned around or something, I'd have a rectangle. And its height is 1 and its width is 10. So the area of the rectangle is 10. So yeah, of course the area of the triangle became half of that, 5. What about this other integral? Well, we should probably distribute there. So, fine, I'm just gonna squeeze it in right there. We need the integral from 0 to 10 of x minus 1/10 x squared dx, which is x squared over 2 minus x cubed over 30. Evaluate of 0 to 10. Now I'm wishing I had actually erased and started all over because I'm having trouble figuring out where to fit it in. Let's see if we can do it here. 10 squared over 2, that's 100 over 2, or that's 50. 1,000 over 30, that's like 100 over 3, that's 33.333. And the difference then is 16.6. Remember that right? With the 6 repeating, just like the 3's repeated. Yeah. So, okay, that's our total moment. I want to take the total moment and divide it by the mass. And I wish I'd worked in fractions instead, but anyway, 16.666 over 5, that's just a little bigger than 3. I guess we could get a calculator and do it. Nah, let's not bother. A little bigger than 3. I bet it's 3 1/3 now that I think about it. So where does this thing balance? There's 5. I just want to try to, yeah. It balances just a little bit to the left of the representative rectangle I drew in there. That's the balancing point. At the ratio of 16.6 divided by 5. Am I right? So there's one integral, but that was just locating the center of gravity of something that we really view as one-dimensional. What about if we have something that's two-dimensional? Right, well, what if we have something that's two-dimensional? That is, you really think there's not just an x-axis, but an x and a y-axis. And you've got some region in this two-dimensional space. I don't know why it would look weird and blobby like that, but we can do this arbitrarily. So I want to think about a particular region. If you work out, the sort of Riemann sum version of figuring out the area of this thing, it basically means draw it over atop of some grid and work out, what that grid looks like. There's a whole bunch of little squares like this that are really going to be delta x by delta y, but let's pass through the whole Riemann stuff idea and think about them as being infinitesimal. So it'll be dy tall and dx wide. Okay? And that little thing weighs some amount. Now, I don't want you to think of this as being cut out of cardboard. I want you to think of this as being really an unusual material whose density depends on position in some arbitrary way. That is, we may have, very light material over here, very heavy material over here. It could, in fact, in aerospace work, when they make composite materials for like spacecraft and helicopters and all kinds of other things, they have materials like this. You can change the density of the thing across its area. So we're going to have a density function rho that is a function of both x and of y. And so what's differential mass in this setting? It's rho of xy times the area, times dA, but I'll call it. I can't decide whether I should call it dx dy or dy dx or dA. Right now I think I'm just going to say dA, mostly because I'm out of space. But it's the same thing, of course, if we're in rectangular coordinates, to say rho of xy dx dy, say. that order might change around if I decided that this integral was easier to do in one order versus the other. That's such a blobby thing. I don't think either integral was very nice. What about our moments? Well, the big deal now is that we have two of them. We have a moment in the y direction, which is how far that piece of differential mass is away from the x-axis. That's the y-coordinate of the point, right? And how far that thing is away from the y-axis, that's the x-coordinate of the point. So there's a little funny business going on in that we call m sub x the moment about the x-axis, but it is, well, differential moment in the x-axis. Differential moment with regard to the x-axis would be y times dy dx. And the differential moment around the y-axis, that would be x times dy dx. So we're going to get moments by integrating, but we'll get two of them, one for x, one for y. We'll get mass by integrating. We'll only get one mass. That is, our actual mass will be the double integral of differential mass, which is to say it's the double integral of rho of xy, dx dy. First, maybe it'd be better to just say over the region. We may have to figure out, we may even have to dissect the region up into nice pieces so that we can turn this one conceptual integral into a bunch of actual integrals that we can calculate. The moment around the x-axis is the double integral over our region of y times rho, not beta. I don't know what that was. Rho of xy. d a. Let's go. And the moment around the y-axis would be the double integral over the region of x times rho of xy dA. Sorry for one bit of writing running almost into the other bit of writing. Let's do a real one here. All right, so let's do a reasonably simple region. I want the part that's above the parabola y equals x squared, but below the line y equals 4. All right, so that's the region in here. So I'm going to ask you to imagine having an object made out of material of variable thickness. So its plan view looks like that. It's just a thing whose area we could easily calculate. But the thickness is going to change on us in a linear fashion. Its thickness at this end is going to be 1 unit thick. But up here, it's going to be 2 units thick. And I shouldn't probably draw a point there. It would be 2 units thick across the whole part of that. So we're making it out of material that's 1 thick here and 2 thick there. It gets wider as we go up. But we can still think of it as a 2-dimensional thing whose density is changing. That's the point. So what would be our rho of xy function in that case if we wanted it? Notice I didn't make it depend on x. So it should just be a function of y. You might want to sort of think about a y-axis and a rho axis. When y is 0, rho is 1. And when y is 4, rho is 2. So there's the function rho of xy, but one, it's, can you tell what the slope of this is? As we move over 4 units, we rise up 1 unit. Yeah, 1/4, and our y-intercept is 1. So rho of xy is 1 plus 1/4 of y. Nice. So can we figure out where this thing would balance? I'm not going to do m sub x. Do you know why I'm not going to do m sub x? Well, because it's really obvious from the symmetry of the thing. Although I'm looking at it more, my picture is really kind of crooked. That y-axis should have been more like up through there, and this thing is at a funky angle. It was supposed to be horizontal. That's worse. Okay, never mind. But still, we know it's supposed to be symmetrical across the y-axis. So I know the CG is somewhere along the y-axis. What I don't know is where it is in there. The fact that it's fatter up here than it is down here makes me think it might be on the high side. And then the thing is wider up here too, so maybe it's really, I don't know. It could be surprisingly high up. Let's do the numbers and see. So first I'm going to need to get our total mass. Remember, that's the double integral over the region of our density with respect to area. So this region, should we do a vertical integral first and then a horizontal, or should we do a horizontal integral first and then a vertical? If you think about it in terms of Riemann sums, we want to add up a whole bunch of things along a strip like that, and then take the sums that we get that way and go, yeah, we do. Because the first integral should be one where the limits are functional, and this limit here is definitely functional. If we went sideways, we'd have to be going between two different ones, square root of something and the negative square root of something, and it's doable, but I think it's easier if we integrate that way. So what is our low limit? It's x squared. And our high limit is 4. And then we'll come on and integrate from across, adding up all of those things that we got by adding strips this way. And that will happen everywhere from -2 all the way to +2 in the x direction. Rho was 1 plus 1/4 y, or 1 plus y over 4. And differential area now is going to be dy dx, because we were integrating y direction first and then x direction first. Cool, so let's do it. When we integrate that expression with respect to y, we get y plus y squared over 2 over 4, that's y squared over 8. Evaluated from x squared is the bottom limit, 4 is the upper limit. Sure, 4 plus 16 over 8, 2. Did I do that right? 4 squared over 8, yeah, that's 2. 4 plus 2, okay, 6. And then we're going to subtract what happens if we evaluate all the y's become x squareds. I guess I just have to write it. It's going to be x squared plus x to the 4th over 8, because it's y squared squared, or x squared squared. Okay, that's what it is. No, it's not, because what have we not done? Darn it. I've got bad equal signs here. Well, I can fix them though. We still need to integrate with respect to x. That was silly. Kind of worried about spacing again. How about if I just steal a little area at the top right of the board so we don't have to erase too much, and finish off this integral. Now we're integrating with respect to x, so 6 becomes 6x. Minus x squared becomes minus x cubed over 3. And minus x to the 4th over 8 becomes minus x to the 5th over 40. There's a 5 from the x to the 5 over 5, and there's that 8. Okay. That's evaluated between 2 and minus 2. Minus 2 at the low limit, plus 2 at the top limit. Something kind of nice happens here because all the x's are appearing with odd powers. So a symmetric interval like this with odd powers in it, you just calculate it at the upper limit and double. Because when you're at the -2 thing, you'll get negative numbers that are equal to what you get when you add +2 in there, but negative. But we're subtracting them because it's the lower limit, right? So, or if we were subtracting, now we'll be adding them. Anyway, wait a minute, did I just say that right? Like, look at the 6x. At the upper limit, you'll have 12, and then you'll be subtracting -12. Well, that's adding another 12, so you get twice as much. Anyway, let's do it. 2 times 12 minus 8 over 3 minus, I have to stop and figure out the 5th power. 2, 4, 8, 16, 32 over 40. Oh, and got a calculator. It's 14.4. And that's not an approximation. It came out 14.4 exactly. So I guess something happened with tenths. I'm surprised because there's this thirds in there. Anyway, yeah, so that's good, 14.4. That's our mass. Now, I've mentioned already, we don't need to worry about calculating the moment in this direction, our distances from the y-axis, because, well, it's symmetrical, so we're going to end up with a position on the y-axis. But in the our moments around the x-axis, we will need to compute. Now, how is that going to look? We want the moment about x, which is a double integral over the region of y times rho of xy dA. We already have set up our integral, which is nice. We know how to do the integral effectively. Go from -2 to 2, and then from x squared to 4, y times the function for rho, which I think I just erased, but it was 1 plus y over 4. Y times rho times differential area, which is just dy dx, and it's in that order, dy dx, as it was previously. Just want to distribute that y plus y squared over 4 dy dx. I've been resisting erasing the diagram, but I think I'm going to do that now. Okay, this time I won't make the same boneheaded mistake I made before. I'm keeping the integral with respect to x. But let's go ahead and do the inside integral. Y turns into y squared over 2. Y squared turns into y cubed over 3. It's already over 4, so that's y cubed over 12. We need to evaluate that from x squared to 4. And then we still need a dx on the end because we haven't done the outer integral yet. All right, at the upper limit, it's all numerics. So 16 over 2 is 8 plus 64 over 12. 5 1/3, I believe. Yep, 5 1/3. What did I say the other one was? 4 squared over 2. That's 8, yeah. Okay, so 13 1/3. At the lower limit, we're going to have x squared squared, or x to the 4th over 2. And we're also going to be having x squared to the 3rd. Wow, that's 2 to the 3rd. 2 times 3, 6. X to the 6th over 12. Wait. That's a lot. It's a high power. Anyway, that all has to be integrated with respect to x. Well, 13 1/3 is going to turn into 13 1/3 times x. That's nice. X to the 4th over 2 is going to turn into x to the 5th over 5 and 2. That's 10. And that'll be x to the 7 over 84. That gets evaluated from, well, let's just play it smart. We again have odd things in the thing, so we get the same result if we go 0 to 2 and double it. Definitely think we want to just use a calculator on this one. So I've got 13 1/3 times 2. I had 13 1/3 in the calculator already. And then we subtract 2 to the 5th over 10. .46 repeating. And then we subtract 2 to the 7 over 84. .94, but then we didn't double it yet, so we need to times 2. 43.8857. I'm just going to leave it at that. 43.8857. More decimal places than we probably need. I probably should have rounded it to 2 or even 3. In fact, gosh, I'm being bad in terms of significant figures right now. I have 6 significant figures. That really feels wrong to me because, how accurately did we know these things? The limits were actually given only to 1 significant figure. I'm going to assuage my guilt just a little bit by rounding this to 3 decimal places. It's not a sig figs approach, but in engineering, they always just keep everything to 3 decimal places. It seems to work. Bridges don't fall down. Okay, so that number was our moment around the x-axis. So if we want to get the distance y bar, we take the moment about the x-axis and divide it by the total mass. I know this feels funky at first, but the y coordinates are the ones that determine how far you are from the x-axis. So moment about x ends up giving you y bar. So this was, well, it's going to be approximated by 43.886 divided by 14.4. I've got this answer still in my calculator, so we'll divide by 14.4 and get 3.047. All right, so now is the point where I was trying to save the diagram, but let's recall what it looked like. We had a parabola, and then the line with a horizontal value at y equals 4. I'm just having the hardest time keeping these lines horizontal. Still not looking great. Okay, if I make it fatter, then you can't tell that my picture is so ugly. Anyway, this thing was going from 0 up to 4, and now we just, and remember the thickness? Here the thickness was 2, no, 1. Up here, the thickness was 2. So it's getting bigger as we go up. And the balancing point, the center of gravity is, let's try to draw it pretty accurately, a little tiny bit above 3. So if we want to make one of those CG symbols here, it would be like that. Right on the y-axis, but almost way closer to the top edge than you might have thought. All right, so the last stage of the complexity that we need to deal with now is to move this all to 3D. What if we have a three-dimensional object, a solid region, and it's got variable density? And that happens, like, for instance, the Earth is like that. The Earth's core is made of nickel and iron, very dense. The mantle is made of molten basalt, and it's not as dense. And the crust is literally floating on that sea of molten basalt, so it's even less dense, or it wouldn't float. There's this changing density all throughout the structure of the Earth, and we can integrate that. Well, we can integrate models of those densities and find out how much our planet weighs. It's fun stuff, science. Anyway, let's see. Here's the problem. Let me try to draw for you a chunk of space, an object, a little chunk of differential mass that's in the first octant. Trying to picture a little dx by dy by dz cubed, but it's somewhere up there in the first octant. So here's the x-axis, there's the y. That was kind of going away from us. Z is up here. If I drop this guy down onto the plane, its shadow would be right there. And that's actually probably the first picture to look at. How far that little cubelet is from the xy plane, that's the z coordinate of it, isn't it? So what we're going to do, if we do a triple integral over the region of z times differential volume, oops, sorry, might be a function of x, y, and z that gives you the density as well, and then dv. What you're going to get when you take the z coordinate times the thing is a measure of how far that little mass is away from a plane, not away from an axis. So that's called the moment from the xy plane. But that's the z coordinate. So when I go to find the z coordinate of the center of mass, it's going to be the moment about the from the xy plane divided by the actual mass. And there's a similar thing for all the other directions. You can think about, what if we integrated x times, I just moved my finger in the direction of y, so let's do that instead. What if we integrated y times the differential mass, that is the density times the differential volume? That'll get us how far we are from the xz plane. So that would be the moment from the xz plane a triple integral over our region of y times rho of xyz times differential volume. So you'll notice now that the pattern becomes a little more clear, actually. The variable that's multiplied on the inside is the one that you don't see amongst the subscripts. That's why there was that backwardness in the moment about x, we integrated y, etc. All right, so what would m sub xz allow us to compute? That would let us get y bar, which would be m sub xz, which we get by double integrating, right? Divided by m. And the m's we also need to get by, I think my lips just said double integrating when I was pointing at something with 3 integral signs. Triple integrating. We get both of these things in numerator and denominator by triple integrating. In fact, to get, there's one more which I think you can tell what it would look like. X bar would be the moment from the yz plane divided by the mass. So there are 3 different moment calculations and 1 mass calculation, all of which are going to be triple integrals over the same volume. So setting up the integral is a job that only has to be done once, and you find yourself using the same setup again and again. So we'll try an example of this with a 3-dimensional object. This is a hemisphere. Let's stick with simple stuff, so we'll make its radius be 1. A radius 1 hemisphere. But so it's a little bit fun, I'm going to make it have variable density. And the density I want to do is have it have unit density down here, tapering off to half a unit density at the top. So that is, the density is in layers. That is, we'll have density 1 down here and getting lighter and lighter and lighter until it's at density 1/2 up here. Now you can actually make that happen if you, for instance, I would probably have this thing inverted, pouring epoxy into a mold, but I would mix different amounts of filler into the epoxy so that I could change the density of it. You might start with a whole lot of polymer beads in it to make it density 1/2. Towards the top, you might be mixing into the epoxy or using some metal to make it even more dense. But anyway, you can sort of slowly fill the mold up with epoxy while changing the density of the epoxy while you go and making it have this strange behavior. But here's the idea. I want rho really to be just a function of z. And when z is 0, we're starting at density 1. And when z is 1, which would be here, we're getting to density 1/2. Oh, it'll shape like that. Well, that's easy to figure out what rho is. Rho is 1 minus z over 2. I'm going to cross my z so you can tell it from my 2. Okay. Now, what about the system of integration? Should we use rectangular coordinates, maybe cylindrical? Of course not. It's a sphere. We should use spherical coordinates. Great. So here's the only problem is I set it up in x, y, z coordinates, and we need to know about the conversions. What are the limits of this thing if we do the triple integral with respect, well, the triple integral in spherical coordinates? This has theta going all the way around, rho going from 0 out to the radius, 0 to 1, and phi going from 0 down to just 90 degrees, or pi over 2. That's a spherical rectangle, or spherical prism anyway. All the limits were constants. So let me just say those again. We said 0 to 2 pi for theta. For rho, it's from, I guess it should be less than or equals 0 out to 1. And for phi, or phi, it's 0 at the North Pole down to 90 degrees, or pi over 2. Since they're all constant limits, we can do the order of integration any way we like, which is nice. What else are we going to need? Well, I need to know what z is in these coordinates. Now for that, we actually, that was part of our last worksheet, but let me at least recall to your mind one little bit of that worksheet. If you're thinking about an angle phi away from the vertical and describing a ray, actually it describes a cone, but we're taking a section right now. Sorry, that phi looks horrible, but you recognize that as being a phi right there. And rho would be how far out we are. Darn, now we're really in trouble, aren't we? Shoot. I've got this rho for radius in spherical coordinates, and I've got that rho for density in regular coordinates. This will never do. Now, we're just going to have to change variables. Pardon me for this, but let's call this density, D. And density there, so as not to mess with the rho from sphericals. Collision of the namespace, as they say. All right, so what is the z coordinate of this point, who's got a particular phi and a particular rho? It's the adjacent side of the triangle here. So it's really rho times the cosine of phi. That's what z is. I think we're in a position to integrate now. Oh, yeah, well, we do have to say, what's the differential volume in this case? Remember, it's rho squared sine phi d rho, d theta, d phi, or some permutation of those last three things. Rho squared sine phi, yeah, that's right. Okay. I think we're ready. I think we're ready. We're going to have a triple integral. I don't believe it's going to matter what order we integrate with respect to, but the things in the integrands are going to be our density, which was 1 minus z over 2, and z became rho cos phi so times, what am I doing so far? I'm trying to get mass. So mass is going to be this triple integral density times differential volume, which is rho squared sine phi d. I don't know. Let's try d rho, d theta, d phi. I'm not sure if there's any sense in doing it in a different order or not. All right, so we just have to simplify this integrand. I guess the main point would be just to distribute that rho squared sine phi across everything else. So rho squared sine phi minus rho cubed cos phi sine phi. I think we want to run half out here. D rho, d theta, d I think that'll be okay. What are our limits? I should have figured out what the limits were up there. The inner integral has the rho limits, which go 0 to 1. The middle integral has the theta limits, those are 0 to 2 pi. And the outside one is 0 to pi over 2 for the phi limits. I was looking at this at first, getting a little bit afraid because there's a lot of complication in there, but I don't think it's all that bad when you actually run through it. When we integrate with respect to rho, the rho squared becomes rho cubed over 3, and sine phi is just a constant, goes along for the ride. And rho cubed becomes rho to the 4th over 4, which is going to end up being rho to the 4th over 8. And then the other things, cos phi and sine phi, again, they're just constants as far as rho is concerned, so they come along for the ride. That whole thing, evaluated from rho is 0 to 1, that's the inner integral. And we still have 2 more integrals to go. 0 to pi over 2 for the phi, and 0 to 2 pi for the theta. All right, so let's do the evaluation. It's nice because the 0 at the bottom limit means we don't have to worry about that, because, yeah, that's rho equals 0 to rho equals 1. So we get 1/3 sine phi minus 1/8 cos phi sine phi. So I had a little malfunction in my other camera. We're going to finish this computation, and actually that's fine, it's the last thing we need to do in a slightly different format. But what we were looking at was, we'd already done the integral with respect to rho, just need to evaluate at the limits, and those give us 1/3 sine phi minus 1/8 cos phi sine phi. Oops, cos phi sine phi, and we are going to integrate that 0 to 2 pi with respect to theta, and then with respect to phi, we will integrate from 0 to pi over 2. Now, the theta integration, all of this stuff doesn't involve theta, right? So you just get that stuff times theta. That is only the d theta involves theta, so you just get theta. Evaluating between 0 and 2 pi, it just pulls up a factor of 2 pi that we need to deal with, and that can come right on out of the other integral because it's a constant. So great, we can take that 2 pi out and then deal with the integral from 0 to pi over 2 of the pieces we saw before. 1/3 sine phi minus 1/8 cos phi sine phi. This integral is with respect to phi. Okay, so I think it's clear that we'd like to split this in two. Integrating sine gives us negative cosine. Now, cosine is 0 at this upper limit, and it is 1 at this lower limit. So we'll be taking 0 minus negative 1/3. Okay, so that's positive 1/3. So that first piece becomes 2 pi over 3. What about integrating 1/8 cos phi sine phi? There's still the 2 pi factor I need to bring along, sorry. Let's bring the 8 outside. I don't think that's going to help us either. Cos phi sine phi. How can we deal with that? I believe a u substitution is in order. If u was sine phi, then du would be cos phi d phi. So we've got u du, we just get u squared over 2. That is u, oh, so u is sine squared phi over 2, evaluated between the limits. 0 to 1. That's going to be slightly ugly. And there was this factor of negative 2 pi over, yeah, we're subtracting 2 pi over 8 times that. Let's just pull that down to where it belongs. 2 pi over 3 minus this thing. Cool. Well, that's going to require just a calculator to integrate, because sine squared of 1, sine of 1, not a nice number. Let me go grab a calculator. All right, so the first part of our thing was 2 times pi divided by 3, which is 2.094. Minus, we need 2 pi over 8, or pi over 4, I should have simplified that before, times sine of 1 squared. Uh-oh. That result makes me think I've got my calculator in the degree mode, so let's just check. Sure enough, make sure you're in radians when you're doing scientific stuff. Okay, so can I just do 0.84, great, to the second power. 0.708. That's what we get at the upper limit. At the lower limit, sine of 0 will be 0. So that's cool. We need that number over 2, and then times pi over 4. .278. So finally, we've got a mass for our guy. It's 2.094 minus 0.278 comes to 1.816. If we want to, we could then get the we need the moment from the xy plane, which would be integrating the z coordinate times this. Yeah, so I just double checked. What we ended up computing just now was our mass, which makes sense, by the way. The value is greater than 1, and we were working on a hemisphere of radius 1, so we expected its, if we were getting the z coordinate of the center of mass out of this thing, we would be expecting a number less than 1, so that's good. I think we'll end this here because there's one more computation to be done, which is the moment from the xy plane, and then we would divide that number by this mass. The only difference in the integrals, that would use all the same limits, but there'd be an extra factor of z, which is rho times cos phi. It turns it into a slightly more difficult integral of trig functions, but it's one that we can still do. And even if we couldn't, we could get a value for it numerically. So let's call it quits there. But let me at least just lay out for you the basic idea. What you do is get your moment from the xy plane, which is a triple integral with all the same limits of z times the density times, well, the differential volume, that's where you include the r squared and the sine phi thing. And then your z coordinate of the center of gravity is going to be this moment from the xy plane divided by the mass, which we just did calculate the mass. That's the 1.816 here. But I think I'm going to let that slide for now so this video doesn't get any longer than it already is. See you tomorrow.